look at chapter 12. And again, we're going to run this preparatory stuff. All right, so what we're going to do here is do text analysis and generation. So we want to count unique words, so we're going to download a book from Project Gutenberg, Dr. Jekyll and Mr. Hyde. And this includes information about the book. We're going to use clean file to remove this material. So the lines that start with star, 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 we're going to remove them. And now this will define the clean file. All right. And so now there's the file name and there's the clean file. All right, and so we're going to read the lines and split them into words and then store each word as a key in a dictionary. All right, and then we're going to print the length of the unique words it finds here. So it's going to count through the whole file, and it's going to only count unique words. So words that are repeated, like the and a will be repeated many times. So 6,000 different words and 42. But you're going to see some of them are not valid words. So we're going to look at the longest words, and we're going to sort it by length and look at the 5 longest words. And there they are, and you can see there are these words with a dash in the middle. Chocolate colored, superiors behold. These are 2 words connected by a dash. They're not really a compound word. All right. So we're going to have to deal with dashes and other punctuation, like this exclamation point too would count as a letter in a word, and we probably don't want to do that. So when a dash appears, we replace it with a space. After splitting the words, we use strip to remove punctuation. So to handle the first issue, this is replace. I use this all the time. Replace all dashes by spaces. All right, that's what split line will do. And so if you run it on coolness frightened, it'll split it into coolness and frightened. Now strip will remove punctuation from the beginning and the end of a word, but the only thing it's going to strip by default is white space, I think. So you have to consider what other characters to remove. Characters in Python are Unicode, and there is a thing called Unicode data to give you the category of a letter. So A is an LU, letter uppercase, and this is a dot is punctuation. So P, so you can use this function to tell punctuation marks from other things. So we can look for characters that begin with P. This will store the unique punctuation marks in a dictionary. It's going to go through every line and then go through every character in the line and then get the Unicode category, and if it starts with P, it will add it here. So we'll get a list of the punctuation marks so we can join the keys of the dictionary into a string. Right, once we have this thing, okay. And so there's the punctuation marks. There really aren't that many. All right. So now we're going to take a word, strip the punctuation from the beginning and the end, and convert it to lowercase. So if we give it behold exclamation point, it's going to remove, just give me behold lowercase without the quotation marks and without the exclamation point. So that's pretty good. And pocket handkerchief should split that into pocket and handkerchief. Oh, it doesn't do the hyphenated words yet. We didn't handle that part yet. All right, so here we're going to use split line and clean word. The split line is what gets rid of the hyphenations. And so this will get us the unique words in the book. And now there's only 4,000. Remember before there were, I think, 6,000. Yeah, so, and we can take a look at the longest words now, and we'll see that now they're all words, except fellow creatures in chocolate colored. Now why, wait a minute now, why are they not split? I'm a little confused by, I thought we were going to get rid of these dashes. I thought that's what this split line did, but apparently not. We never got rid of the dashes yet, okay? I'm a little unclear on that, but anyway, here's the word frequencies of each unique word. Did I forget to run something? No, I don't think so. All right. I thought we were going to get rid of those dashes, but apparently not. All right, now we'll get word frequencies. For each word, you just count. If it's not in word counter, you add it with 1, otherwise you increment it. So now you're going to get the frequency for each word. And see which words appear more often, we can use items and sort them. This is going to get the second element. Okay, I thought we already had that, but now we have it again. Now we can do sorted by the second element, reverse, to put the most common one on top. And so we can print the top 5, and there they are. Well, as you'd expect, the, and, of, to, and I are the most common words. That makes a lot of sense. All right. So we used built-in functions. Now you noticed optional parameters, like round takes an optional parameter called n digits that indicates how many places to keep. So here you have round to 3 places, but if you run it without n digits, then if you don't specify n digits, I think it defaults to 2, but let's find out. All right. Somebody get this thing to shut up. Let's run it. Still doesn't shut up. All right. There. So now, I guess it rounds to an integer. All right. If you don't tell it, it rounds to 0 digits after the decimal place. All right. But you can write functions with optional parameters. And what you do here is a most common word with word counter and num equals 5. This thing where you set it equals to 5, now you have a parameter you can specify, but if you don't specify, it will switch to the default value. So this will print the most common certain number of items by sorting them and then printing them. So now I can print the most common, and it'll just print the top 5. But if I add an argument like 3, then it'll print the top 3. So that's useful, having an optional parameter. All right. If it has both optional and required parameters, all the required parameters have to come first. You can't do this, n equals 5 and then word counter. It won't let you do it. Parameter without a default follows parameter with a default. All right. Now you can do dictionary subtraction. You're going to find words that might be misspelled. So you find words that don't appear in a list of valid words. So here we're going to download some list of words that are valid, and we can read the contents and split it into strings, and then store them as keys in a dictionary. All right, so that in will run very fast. And now you identify words that appear in the book, but not the word list. So for key in D, there's 2 lists. The keys that appear in this list, but not in that one, are what you're going to find here. So the key is in here. If it's not in D2, then add it to res and return res. Those are going to be the suspicious words that are not in my list of known good words. And so now that subtracts, we're going to subtract word counter valid words. That should do it. And let's print the most common. Here's the words that might be misspelled. And I probably because it should be capitalized. I don't know why A is not there. Okay. Single letter words. Perhaps their list of known good words didn't include I and A. Mr. probably should have a dot. And these look like misspelled names. This one's misspelled. That's an unusual name. All right, anyway, I guess it's a real name. Proper nouns, that's reasonable. They don't appear there. So these are things that are many times wrong. That's probably not a misspelling because you wouldn't misspell it 124 times. So it's the least likely ones. So we're going to get the ones only with a frequency of 1. Those are the singletons. And here's the last few elements of that list. Okay, gesticulated, abjection, circumscription, re-and-do. That looks like and fear struck. Okay, so these are just unusual words. This is some kind of misspelling, and that should have a dash or something. All right. Anyway. All right. And so another thing you might want to do is have it pick random words. So randomness is a real problem in computing. There was a vulnerability that came about 12 years ago where someone decided, I think a Canadian researcher, downloaded all the HTTPS certificates on the web and then saw how many of them had a common factor. They were RSA certificates, so they were supposed to have a number that was the product of 2 prime numbers, but some of them could be divided. So that means he found that like 1 in 1,000 of all the keys on the web shared a prime factor. And they wondered what caused that, and they eventually tracked it down to devices like firewalls that would boot up and then create a random number, and another copy of the same firewall from the same manufacturer would boot up and end up creating exactly the same random number because they used something like the number of microseconds since you turned on the power, as the seed for the random number generator, and another firewall built by the same manufacturer might take exactly the same number of microseconds to boot up. And that's the huge problem. There's nothing random in a computer, so it's hard to make a random number. Now, to solve this, the Intel processor recently has a built-in hardware random number generator, which is a resistor which amplifies the Johnson noise. Resistance in resistors varies because the atoms move randomly, and so that's supposedly a high-quality random number generator. But in general, it's a problem. Computers are deterministic, so how do you get a random number? That's quite difficult, so we use tricks to fake it. They're not truly random, but you try to include several things like clocks and things that measure the input from the user and such. Anyway, there is a function called random that you can seed it with a number, and then it will create a whole series of pseudo-random numbers starting from that seed, but if you know the seed, you can predict them all. So we're going to seed it with 4, and now we're going to choose these elements, and we'll choose it for 1, 2, and 3. All right, so if we call it again, we'll get a different element. First time it picked the 1, next time it picked the 2. All right, if you try to give choice and feed in a dictionary, you'll get a key error. You're not allowed to do that. To choose a random key, you have to put in the keys in a list and then call choice. So you make a list of them, and then you make a random choice here, so it'll pick a random word out of there. So you can generate a random series of words, and of course, that works, but it's not making any sense. All right, so it'll be better if you choose words with weights to choose the more common words more often. And by the way, you might notice that what we're doing here is the steps that would lead to eventually these large language models that can create good readable looking text. This is some of the very simple steps in that direction. So you're going to count, you're going to have weights that count how often those words are used. And then you can make choices that are weighted. So it's not that it chooses one word with an equal chance for each of the words, but you can feed in weights. And so now you see it picks a more common word, which is more likely. And you can have another argument that shows the number of words to select. So now I'll get reached right. It still doesn't make much sense, but at least it shows more common words here. And you can join them to make something that looks a little bit more like a sentence. All right. Now the next thing would be to have patterns of words, like the should be followed by an adjective or a noun. So you can look at sequences of 2 words, which are called bigrams. And so you can make a bigram counter. This will take 2 strings as a list of 2 strings. It'll make a tuple of the 2 strings. Then it adds the key to bigram counter. Okay, so if I feed in all pairs of words, this is going to count how often those different pairs of words occur. So as you go through the book, we're going to have a sliding window that goes over the book showing 2 words at a time. So here's a window, and now we're going to append the word, and to process words one at a time. Window append. If link window equals 2, then count the bigram. Otherwise, pop off the first word. Okay, so this will read the words, add it until you have a pair, count the pair, then throw away the first word and put in a new second word, and so on. That makes sense. All right, and so now we're going to feed it all the data from the file, and we're going to see the most common pairs, and so of the, in the, it was, and the, to the. Okay, so those are the most common pairs of words in the order in which they come. All right, so now you can have random seed, and now you can pick random bigrams to generate random text. And now you can sample according to those weights. And now you get to suggest, this preface to detain, fact is, above all. Now each pair, the words are kind of in a logical sequence, but there's no logical relationship between the pairs. All right. And this is, like I say, very much what happens in large language models. In large language models, you include a larger bit of context, like 100 words before and after, and you try to guess a word in the middle. And you train it to guess the word that it fits in context best. And this is how large language models work. They can produce a page of text that reads as if a human wrote it. It appears to make sense, but the computer program has no actual intelligence and it doesn't understand what any of the words mean. It doesn't know what it's saying. It just knows how to make the words look like the words you'd expect to see. So you get a paragraph that looks pretty easy to read, and it really is just sort of the average of paragraphs it found on the internet while learning. All right, so here's a song from Monty Python. And so we're going to use a dictionary that maps from each word to the list of words that follow it. So here's the two words of the song, half a B philosophically, half A. All right. So one possible successor from the first word is the second word. So half can be followed by A. That's one thing that comes after it. Okay. If the first word is already in the dictionary, we can look it up to get the successor and append the new one. Okay. And so half not is something that's going to happen, or is it? Half the B. Half not, yep. So half is going to sometimes have A, sometimes have not, and sometimes have the. So we're going to have half can have either of those words after it. And so this will encapsulate those steps. And all right. We're going to keep track of how many times each successor appeared. So we process the words in the string and get these results. So half can go to here, A can go to there, B can go to there, and so on. So now you have a record of what the next word should be, of what the various possibilities are. All right. Now you can analyze the book in the same process. And you can look up any word and find the words that follow it. So story can be followed by those words, incident can be followed by those, and so on. All right. And there's a successor map. All right. So this is the kind of stuff you do to do. This kind of thing is done to break cryptography is one way I know. This, you look for patterns of words, and then you look for patterns in the ciphertext. All right, so now you can generate some text with the same relationships. Starting with any word, we look up its possible successors and choose one at random. Then we use that word and choose it at random, so we can generate as many words as we want. And so we'll start with the word although, and then follow with some words. Seeding the random number generator, we can now choose, okay, and repeating these steps, we can use this to generate a longer series. Continue to hesitate and swallowed the smile withered from that. It's starting to make a little bit of sense this way. Now, each word at least is reasonable to follow the word right before it, but there's no larger scale structure here. All right, you can do better by using more than one word in there and so on. And in large language models, they take whole sentences and compare it to the next sentence, and then half the time they replace the next sentence with the wrong sentence, and they train it to know which sentence fits in better. So that gives it the longer coherence that makes it able to go through paragraphs and stay more or less on topic. All right, and so if you want to find problems, you can read the code, you can experiment. What I often do is add a lot of print statements to it to print the partial products to figure out what's going on. And of course, if you get an error message, you can Google the error message. It will often help. Explain the problem to someone else. Bounce it off another person. They might see your problem. Often you back up to a version of your program that works. I've done this a lot. And then start again. And often just giving up and waiting for another day so you get a fresh attack is what you have to do. All right. So that's the summary of that one. I'm going to stop this recording.